Welcome back to the deep dive, your shortcut to being genuinely well informed on the topics that, well, really matter. Today, we're plunging into the pretty fascinating world of high performance computing and AI infrastructure. We're going to peel back the layers on some critical challenges and some pretty elegant solutions, too. Our source material for this deep dive is actually incredibly insightful. It's a collection of practice questions and their detailed explanations from the NVIDIA Certified Professional AI Infrastructure exam, the NCP-AII. Now, look, we're not here to prep you for an exam, right? We want to do something I think far more valuable. Extract those core nuggets of knowledge, those aha moments, the things that explain why things work, and maybe more importantly, why they sometimes just, unexpectedly don't work in these complex GPU environments. This is about giving you practical, actionable insights.
Yeah, and what's really fascinating here, it's not just about the questions themselves. They're not just theoretical puzzles. They are, they're a direct mirror of the most common real-world challenges engineers face every single day.
Mm.
Deploying, optimizing, troubleshooting AI workloads with NVIDIA hardware. So we're going to go way beyond just saying this is the right answer. We'll connect the dots, look at the broader implications, and really reveal the crucial context for you, the listener. So you can actually use this stuff, hashtag IFE, optimizing GPU performance and driver management.
Absolutely. So let's kick things off with a classic scenario, something that can drive any engineer a little nuts, an application that's just not starting fast enough on your GPU. So you're monitoring things, maybe using NVIDIA SMITE, the NVIDIA System Management Interface, kind of your command line dashboard for the GPU, and you notice that persistent mode is off.
Yeah.
So our first question asks, what is the main benefit of enabling persistent mode? In these high-performance setups where every millisecond counts, what's the real game changer here? Why is this setting so critical?
That's a great real-world scenario. The core insight here, really the aha moment for persistent mode, is that it keeps the GPU driver loaded in memory, even when no applications are actually running. And that significantly reduces application startup latency. The key takeaway is really minimizing overhead. Think of it like preheating your oven, right? You wouldn't wait for it to warm up after you put the cake in.
Right.
It's the same idea. Keeping that GPU driver resident means your app starts almost instantly. Super important for microservices, rapid inferencing, any of those high-frequency tasks where, waiting just kills the user experience or runs up your cloud bill.
Okay, that clarifies it perfectly, preheating the oven for your GPU. I like that. So if it offers such a clear benefit, are there any downsides? Anything engineers should be aware of, even minor stuff? Or is it pretty much an always-on thing in these AI environments?
Yeah, it's generally recommended to have it on for, any frequently used or production GPU. The downside, if you even want to call it that, is maybe a tiny increase in memory usage because the driver stays loaded. But honestly, compared to the performance gains, the latency reduction, that minor memory footprint is almost always a worthwhile trade-off. You definitely want it enabled in most production setups.
Got it. That's a sharp distinction. Probably saves a lot of headaches. Now let's stick with drivers for a sec because, well, things can get tricky there. What happens when you do a routine driver upgrade seems simple enough and suddenly your carefully built application just breaks? Our sources highlight a surprisingly common compatibility issue here. The question is, you are upgrading an NVIDIA driver to a new version, but after the upgrade, your application has compatibility issues. What is the most common potential cause? What's usually the culprit in this all too common scenario?
Right, this brings up that whole software version alignment thing, and yeah, it happens all the time. The most common cause, almost always, is that the application uses an outdated CUDA library version that is incompatible with the new driver. It's kind of like trying to play a brand new 4K Blu-ray on an old DVD player.
Yeah, okay.
You've got the shiny new driver, but if the software your app's compiled CUDA library was built for a different, older standard, you're going to get errors, maybe crashes. The driver in your application's CUDA environment absolutely have to speak the same language. It's not just about having the latest driver. It's about having the right driver for your entire software stack.
That is such a crucial point, just recognizing that the ton could save hours, maybe days of painful troubleshooting. Okay, so you're running along, things are working great, then bam, you hit that dreaded out of GPU memory error under heavy load. Feels like the GPU just threw its hands up, right? I can't take anymore. But often you can just run out and buy more hardware immediately. So how do you fix that without breaking the bank? Our practice question asks, your AI service encounters an out of GPU memory issue under heavy load. To resolve this without adding more hardware, how would you optimize the workload? What's the go-to strategy here?
Well, the fundamental takeaway, the immediate thing you can usually try, is decreasing the model's batch size. It directly tackles the problem by making each chunk of data you process smaller. So instead of trying to process, say, 64 images at once, you might drop it down to 32 or even 16. This drastically reduces the memory needed for each training step or inference call. It's basically smart resource management, right? It lets you sit within the memory you already have without needing those immediate, often costly hardware upgrades. It's usually the first line of defense for these memory-bound issues.
That makes perfect sense for just, fitting inside the memory limits. But does decreasing the batch size have any other impacts, like on the training process itself, maybe training time or model stability?
Oh, absolutely it can. Yeah, that's a great question. While it solves the memory problem, a smaller batch size means you're updating the model's weights more often. That can sometimes lead to noisier gradients, maybe a less stable training process, or potentially slower convergence for some models. But conversely, it can also act as a kind of regularization sometimes. So you might need to adjust other things, like your learning rate or the number of training epochs, to compensate. It's definitely a trade-off, but often it's the necessary one just to get the model running at all. Then you can fine-tune the other bits. #tag 22, high-performance storage for AI workloads.
All right, so we've looked at optimizing the GPU itself, ironed out some driver kinks. But, a super fast GPU is still kind of useless if it's just sitting there waiting for data. So let's talk about the next big bottleneck,
Yeah.
feeding these data-hungry beasts effectively. Our next point hits on a crucial piece for that, high-performance storage. If you're setting up storage for an AI workload and you absolutely need to minimize those data transfer bottlenecks, what's the best solution for the kind of high bandwidth, low latency demands GPUs have? The question puts it like this. You are configuring storage for an AI workload and need to minimize data transfer bottlenecks. Which storage solution is best suited for satisfying the high bandwidth and low latency demands of GPUs? What should engineers be really prioritizing here?
Yeah, what's critical to get here is just how different traditional storage is from what GPUs really need to stay busy.
Yeah.
I mean, GPUs process data incredibly fast. If the data isn't arriving fast enough, they just sit idle. They're effectively starving, right? Wasting really expensive compute power. So the standout answer here is a high-speed parallel file system or local NVMe storage. Things like NAS, network-attached storage, or just standard cloud object storage. Well, they're convenient for other things, sure, but they just introduce unacceptable bottlenecks for these really demanding, high-throughput AI workloads.
Yeah.
You absolutely need the raw bandwidth and that ultra-low latency these specialized solutions give you. Keeps the GPUs fed.
That paints a pretty vivid picture of GPU starvation. Nobody wants that. Are these high-speed parallel file systems or NVMe solutions, are they typically more complex or costly to set up compared to, say, a standard NAS?
Oh yeah, they absolutely can be more complex and, yes, often more costly up front.
Hmm.
Parallel file systems, they need significant expertise to design, deploy, manage. Often involves dedicated networking, specialized hardware. Local NVMe is even faster, but then the storage is right on the compute node. That can create its own challenges for sharing data or managing it across a whole cluster. So it's a balancing act. You're trading off maybe ease of deployment and cost for that sheer performance. It's a trade-off that's becoming more and more necessary as AI models and data sets just keep getting bigger. #3T, Kubernetes and GPU orchestration. Okay, now let's dive into Kubernetes. It's kind of become the default orchestrator for so many AI deployments these days. And it brings its own set of, well, fascinating, sometimes frustrating challenges. What happens when your pods are failing to start? You get that message like, could not find necessary video libraries for GPU. It's a common kind of cryptic error. Our question lists multiple potential causes. Pods in your Kubernetes cluster are failing to start with the error, could not find necessary NVIDIA libraries for GPU. What factors could be causing this issue? When you see that error, what's your sort of mental checklist? Right, this really asks, what are the foundational layers you actually need for GPU compute inside Kubernetes? And it's almost never just one single thing, which makes it tricky. My mental checklist, it includes three main culprits. First, the NVIDIA drivers might just not be installed on the host node itself. That's step one, right? Hardware needs its software.
Basic stuff.
Totally. Second, the container image your app is running in might be missing the required CUDA libraries. Your app expects a certain CUD version, and it's just not there inside the container. And third, the NVIDIA container runtime might not be correctly configured on the host. This is that crucial bridge, basically a special container runtime that teaches Docker or Containered how to see and use the host's physical GPUs inside your containers. Any one of those missing pieces can lead to that frustrating error.
That's a fantastic breakdown of the layers involved. Really highlights the complexity, doesn't it? Debugging these distributed systems when so many bits have to line up just right. So, building on that, What are the absolute essential conditions for any Kubernetes pod to successfully use a GPU? Just making sure all the fundamental pieces are there before you even hit deploy, the question asks. To ensure that a Kubernetes pod can use a GPU, which of the following conditions must be met?
Yeah, I kind of think of these as the three pillars of GPU scheduling in Kubernetes. First, pillar one, a compatible NVIDIA driver must be installed on the host node. Without it, the GPU is just, well, expensive silicon. Invisible to the OS. Second, the NVIDIA device plugin needs to be installed and correctly configured in the cluster. This plugin is the critical piece that finds the GPUs on the nodes, tells the Kubernetes scheduler, hey, these resources are available, and manages them. And third, your pod's definition, the YAML file, must explicitly include an nvidia.com/GPU resource request that tells Kubernetes, hey, scheduler, this specific workload needs a GPU. It really is a delicate dance between these components. If any one of them is out of step, your GPU just won't get used.
A delicate dance indeed, and if any of those pillars are shaky or missing, the whole thing kind of falls apart. Okay, last one for Kubernetes for now. Let's talk performance isolation. This is super critical in multi-tenant clusters, right? Where different teams or apps share the same hardware. Besides using MIG, multi-instance GPU, which is that cool hardware feature for partitioning a single GPU, what other Kubernetes features can help achieve strong GPU isolation? This is more about software-level strategies. Our question is, you need to create strong GPU performance isolation for a multi-tenant Kubernetes cluster. Besides using MIG, multi-instance GPU, what other Kubernetes features can help achieve this goal? And just to clarify, pod affinity, which is about where pods run, isn't really about isolating performance itself. So what are the key software tools and K8s for this?
Yeah, this gets into really important design patterns for making shared GPU environments secure, stable, and efficient. Beyond MIG, you definitely want a multi-layered software approach. First, using separate namespaces for each team or tenant, that's foundational. It logically isolates things, prevents accidental interference, makes management easier. Second, you need to implement resource quotas to limit the number of GPU resources each namespace can actually consume. This is vital. Stops one tenant from hogging all the GPUs, prevents those noisy neighbor problems.
Okay.
And third, enabling network policies to control communication between pods is also crucial. It isolates network traffic so one tenant's busy network activity doesn't mess up another's performance or create security risks. It's really about managing the whole environment, not just the GPU itself, to ensure everyone gets fair and predictable resources.
So it's like a layered defense, basically. You don't just rely on one thing, but use Kubernetes' own tools to build up that robust isolation. That's a really powerful approach. #TagTag AV, NVIDIA Bluefield DPU, and network offloading. All right, let's shift gears a bit. Let's talk NVIDIA's Bluefield DPU's data processing units. These are all about offloading network tasks from the main host CPU, right, to free up those cores for the actual AI work. So let's say you suspect your host's network speed isn't improving like it should, maybe because network offload isn't actually enabled on the DPU interface. How do you check that? Our question asks, when working with an NVIDIA Bluefield DPU, if the host network throughput is not improving and you suspect network offload is not enabled, which command would you use to check the offload settings for the DPU network interface? What's the command line magic for confirming this?
The command you absolutely want is ftool-k. That's your go-to for this specific task. ftool is a standard Linux tool for looking at and controlling network driver and hardware settings. And that -k flag specifically shows you the offload capabilities and, more importantly, the current settings for a network interface. So in a context of a Bluefield DPU, this is the right, most direct way to check if those crucial network offload features, the ones meant to cut host CPU load and boost network performance, are actually turned on and set up like you expect. You wouldn't use like NVIDIA SMI or general system tools for this very specific network function check.
Got it. ftool-k. That's a really specific and powerful command to know. Like you said, knowing the right tool for the job is half the battle sometimes. Okay, and specifically when you want to offload the entire TCP/IP stack from the host CPU onto the DPU, which Bluefield DPU mode is the best fit for that, it's about picking the right operational mode to really unlock the DPU's power. The question states, you are using an NVIDIA Bluefield DPU and want to offload the TCP/IP stack from the host. When configuring the DPU, which mode is best suited for this task?
Right, for that specific goal, Ethernet pass-through mode is the one. It's explicitly designed for exactly this, offloading networking functions, including the whole TCP/IP stack, from the host CPU straight to the DPU. This is absolutely key for getting those big CPU load reductions and the corresponding network performance boosts. By basically delegating all that heavy lifting of network processing to the DPU, You free up your main host CPU to focus entirely on its main job, which, in AI, means more cycles for running your models.
So it's all about shifting the burden, making sure the right hardware is doing the right kind of work, optimizing the whole system architecture. Makes sense. Hashtag via your held.
InfiniBand network troubleshooting. Okay, finally, let's turn to those super high-speed InfiniBand networks. You see them a lot in HPC and large-scale AI clusters. What's your go-to tool when nodes just can't talk to each other, and you have a strong hunch it might be physical stuff like cables or connections? It's tempting to just reach for ping or something familiar, but sometimes you need something much more specialized for the job. The question asks, you are inspecting an NVIDIA InfiniBand network and find that some nodes cannot communicate with each other. When diagnosing physical and cabling issues, which tool is the best choice?
Yeah, IBDAGNet is absolutely the standard diagnostic tool for InfiniBand. This is a really crucial distinction. It's built specifically to help find issues with physical connections, the cabling itself, and the overall topology of an InfiniBand fabric. General TCP/IP tools like Ping or Netstat, they just won't work here because InfiniBand operates at a totally different layer, uses a completely different protocol stack.
So this is a classic case of needing the right specialized tool for the specific technology you're dealing with. IBDAGNet helps you quickly pinpoint the root cause in these high-performance networks where really every single link in the chain matters.
That's a fantastic reminder. Not all networks are the same, and knowing the specialized tools for the specific tech you're working with is, well, paramount. It's the kind of knowledge that can save you hours of just banging your head against the wall using the wrong diagnostics. Hashtag tag outro.
Indeed. This whole deep dive really underscores that smooth AI performance, it isn't magic, right? It's a careful, deliberate orchestration. Hardware, drivers, storage, networking, smart resource management, all working together across multiple layers. What's really fascinating is just how many seemingly separate pieces need to align perfectly for everything to work well, reliably. It's such a complex, interconnected ecosystem. So what does this all mean for your next big AI project?
Well, perhaps it highlights just how crucial it is to think about the entire stack, from the physical cables and network offload settings all the way up to the container runtime, the driver versions, not just the GPU itself. And thinking about that right from the beginning, where might one small oversight in, a seemingly minor area create this ripple effect across your whole infrastructure, impacting performance or reliability later on? It's a powerful thought to carry forward, I think.
Exactly. The devil, or maybe the solution, is often hiding in those details. Keep digging, keep learning, and we'll see you on the next deep dive.